In this video, we'll be solving several problems in periodic motion and simple harmonic motion. So for our first problem, we want to determine the period, frequency, and angular frequency of the second hand and minute hand of a clock. So our second hand ticks at every second, and so it's going to take 1 minute or 60 seconds for it to go all the way around the clock. And so the period is just 1 minute or 60 seconds. And our frequency is 1 over the period, or 1 over 60 seconds. And that is going to give you 0.0167 hertz. So keep in mind that with frequencies in a chapter like this, you may have very high frequencies. And so you may get periods of fractions of a second, even milliseconds. But when you are calculating the frequency from the period, you want to make sure you have your period in seconds in order to get hertz. And then our omega is just 2 pi times the regular frequency, or 2 pi times 0.0167 hertz. And that gives 0.105 radians per second. So now if we move on to the minute hand, the minute hand has a period of 1 hour. So it ticks every minute. And so it takes 60 minutes or 1 hour to go around the clock. So that's the same thing as 3,600 seconds. The frequency is going to be 1 over the period, or 1 over 3,600 seconds. And that's going to equal 2.78 times 10 to the minus 4 hertz. And finally, the angular frequency is 2 pi f, or 2 pi times 2.78 times 10 to the minus 4 hertz. And that's going to equal 0.0017 radians per second. In the next problem, we're going to determine the amplitude, period, frequency, and angular frequency of the periodic motion represented by the graph. So the first thing we can get is the amplitude. So this is just the maximum distance away from equilibrium. So if 0 is equilibrium, then our maximum displacement from equilibrium is just the distance from 0 to the peak, or 0.4 millimeters, which would be 0.0004 meters, or you could write that in scientific notation. The period is the time for it to go from peak to peak or trough to trough. So either of these would be the period. If you start anywhere else, you not only need to go to that same location, that same height, but you need to be going in the same direction. So you wouldn't want to stop here. You would want to stop here. And this would be a full period. But those for this graph don't line up along a number on the t-axis. So we'll just use one that's easy. So we'll do this top, peak to peak. That's going to be 4 milliseconds minus 2 milliseconds, or a 2 millisecond, or 0.002 second period. The frequency is then 1 over the period, 1 over 0.002 seconds. And that comes out to 500 hertz. And finally, our omega, or angular frequency, is just 2 pi times the frequency, or 2 pi times 500 hertz. And since it's angular frequency, I'll just leave this as 1,000 pi radians per second. If you wanted to plug that in, you could plug that in your calculator and actually get a number. For the next problem, we have a 3 kilogram block that's attached to a horizontal spring and oscillates back and forth across a frictionless surface. If the spring has a spring force constant of 640 newtons per meter and the block oscillates with an amplitude of 45 centimeters, find the block's maximum speed, maximum acceleration, and total mechanical energy. So I'm going to start by writing everything that was given that I know. The mass is 3 kilograms. Our spring constant K is 640 newtons per meter. And our amplitude is 45 centimeters, or 0.45 meters. So the first thing we can get is the max speed. So we just have an equation for that. So Vmax is the amplitude times the square root of K over M. which is 0.45 meters, times the square root of k, 640 newtons per meter, over the mass, 3 kilograms, and that comes out to 6.57 meters per second. And then our maximum acceleration, well, this is just the equation for acceleration we get from using Newton's laws and the spring force that's acting on the block. So we get minus k over m times the displacement x. And here, the acceleration is maximum when we are at minus the amplitude. So the minus sign just means we're going in the positive. This will give us an acceleration in the positive x direction. So when we plug that in, we get minus 640 newtons per meter over the mass, 3 kilograms, and minus 0.45 meters for the amplitude. And that gives us 96 meters per second. So if you had plugged in just the positive amplitude, you would have gotten the same number. It would just be negative, so it would be your minimum acceleration or your maximum magnitude acceleration, just going to the left. And then our total energy is, if we know our amplitude, we can just write this as 1/2 Ka squared, where A is the amplitude. Okay, so this is when the energy is all potential energy. And that gives us 1/2 640 newtons per meter times 0.45 meters squared. And this comes out to 64.8 joules. The next problem, we have a box with a mass of 4.3 kilograms that is attached to a horizontal spring and oscillates across a smooth, frictionless surface. The spring has a spring force constant of 250 newtons per meter. If the block is moving at a speed of 13 meters per second when it passes through its equilibrium position, determine the amplitude and maximum acceleration of the block, and finally determine the maximum force that's on the block. So I'll start by writing what I know. The mass is 4.3 kilograms. Our spring constant is 250 newtons per meter. And our maximum velocity is 13 meters per second. So our energy, since we know V max, the maximum velocity will occur when all of the energy is kinetic energy, so there's no potential energy. So that means our total energy will be given by 1/2 mv squared, but our velocity will be V max. And so this is 1/2 4.3 kilograms times 13 meters per second squared. This gives us a total energy of 363.4 joules. So now that we have this, we can use our other expression for energy. So we know all of this kinetic energy is going to turn into potential energy when the oscillator or the mass is at the amplitude. Okay, so then it's going to stop. The spring will be fully stretched or fully compressed, and it will be all potential energy. So now we can take this expression for the energy, 1/2 Ka squared, and solve it for the amplitude. Okay, so we'll multiply by 2, divide by K, and take a square root. So we'll get 2e over K. So this will be square root of 2 times the energy we just found, the total energy, over 250 newtons per meter. And this gives us an amplitude. So now we have amplitude is 1.705 meters. So now that we have the amplitude, if we want the maximum acceleration, well, the maximum acceleration occurs when we are at minus the amplitude. Okay, so this is our expression for the acceleration, minus k over m times x. But we need to plug in minus the amplitude for our displacement. So this will be minus our spring constant k, 250 newtons per meter, over 4.3 kilograms, times minus 1.705 meters. So our maximum acceleration is 99 meters per second squared. And now for our force, we know the maximum force will occur when the acceleration is max, because this force is what's producing that acceleration. So this is equal to minus kx, just our spring force. And so if acceleration is max when x is equal to minus the amplitude, that must also be when our force is max. So for x, we'll plug in minus the amplitude. So this will give us minus 250 newtons per meter times minus 1.705 meters. And we'll get the maximum force is 426 newtons. For the next problem, we have a 0.45 kilogram block that is attached to a horizontal spring and oscillates across a frictionless surface. If the block's period of oscillation is 0.30 seconds and amplitude is 0.22 meters, determine A, the block's velocity as it passes through equilibrium, the total energy of the system, the spring constant of the spring, and the maximum acceleration of the block. So again, I'm going to start by writing what I know. I know the mass is 0.45 kilograms. The period it gave me is 0.30 seconds. The amplitude is 0.22 meters. Okay, and so the first thing I want to solve is the block's velocity as it passes through equilibrium. So the block's velocity when it passes through equilibrium is maximum. This is when there is no potential energy and all of the energy is kinetic. And we know our formula for the velocity, for the maximum velocity, is the amplitude times the square root of k over m. So we have the amplitude and we have the mass, so we need to find our spring constant k. So in order to find k, we're going to use the frequency. So our formula for frequency is F equals 1 over 2 pi times the square root of k over m. So now if we just solve for k, first I'm going to square everything, get F squared equals 1 over 4 pi squared, and then everything in the square root will just come out, k over m. And now I can solve for k. So k equals multiply by 4 pi squared to get it to the other side. And then I'll also multiply by m. So I'll get F squared times m. And now the frequency, I don't know it, but I know the frequency is just 1 over the period. So I can substitute and make this 4 pi squared times m. And for the frequency squared, I'll just get 1 over the period squared. So now I have all of these things and I can solve for k. So this will be 4 pi squared, just a number. Our mass is 0.45 kilograms over the period squared, which is 0.30 seconds. So this gives us a spring constant of 197 newtons per meter. So what I did was I found an equation that had what I needed, k, and it also had things that I knew, namely mass, and I knew I could get frequency from the period. So you could also start with your equation for the period if you happen to have that. So now that we have k, we can come down here and plug in. Our amplitude is 0.22 meters. The square root of k, or 197 newtons per meter, over m, which is 0.45 kilograms. And this gives 4.6 meters per second for our maximum velocity. Now the total energy, now that I have found the maximum velocity, I know the total energy is all kinetic when velocity is maximum as it passes through equilibrium. So this will be 1/2 mv max squared, or 1/2 times 0.45 kilograms times the velocity we just found, 4.6 meters per second, all squared. And that gives a total energy of 4.76 joules. Now I want to find the maximum acceleration. So the acceleration is just equal to minus k over m times x, but acceleration is max when we're at the amplitude, when the string is the most stretched. And so A max is equal to minus k over m. We're going to put in minus the amplitude because we want it to be a positive number. And so if we plug this in, we get minus 197 newtons per meter for k over the mass, 0.45 kilograms, times minus the amplitude minus 0.22 meters. That gives us an acceleration of 96.3 meters per second squared. The next problem, we have a simple pendulum that takes 0.75 seconds from the time it is pulled back and released to its max height reached on the other side or the other end of its swing. Determine the length of the pendulum and how long would it take this pendulum to move from through the same motion on the moon. So first let's write down what we have. This number, this time, 0.75 seconds, this is the time from it being released at one end until it gets to the other. But it doesn't swing back, so this is actually half the period. So half the period is 0.75 seconds. That means for it to swing and then swing back, or a full period, would just be multiplied by 2 and get 1.5 seconds. So now if we want to find the length, we can just use our equation for the period of a simple pendulum. And that's t equals 2 pi times the square root of L over G. And so now if we solve, I'll just square both sides, go through some of the algebra. This will go to 4 pi squared times L over G. Then we can solve for L just by multiplying by G and dividing by 4 pi squared. And we get t squared over, or t squared times G, divided by 4 pi squared. And if we plug in, we have 1.5 seconds for the period, 9.8 meters per second squared for gravitational acceleration, and 4 pi squared on the bottom. That gives us a length of 0.56 meters. Now, if we want the time it takes on the moon, we want it to go through the same motion. So we want half of the period on the moon. Okay, so we need to take our formula for the period, 2 pi times the square root of L, which is going to stay the same even on the moon. But now we need to use gravitational acceleration of the moon. But this is just the equation for the period. We also need to divide by 2. So that's going to lead to these canceling. And then half the period is going to equal pi times the square root of the length, 0.56 meters, divided by 1.625 meters per second squared. So you could just look this up. This is G for the moon, roughly a sixth of what it is on Earth. And this gives you a time of 1.84 seconds. So you could also just solve for the period and then divide it by 2 at the end if you prefer to do it that way or if it makes more sense, but this is what you should get. The next problem, we have a block that is attached to a horizontal spring and oscillates back and forth across a rough surface. The motion of the block is shown in the graph below. If the spring has a force constant of 400 newtons per meter, determine the original energy of the system, the times when the block is not moving, the times when the block is at its equilibrium position, and the energy lost during its first full oscillation. So this is a damping problem. You have a damped oscillator where the oscillator is losing energy to friction. Okay, so the first thing we want to find is the initial energy, so I'll put E naught. And the initial energy is just given by the amplitude at the beginning. So initially, when it was pulled back and released, all of the energy was potential energy in the spring before it started moving. And so it's at its highest right here. And so our total energy is just 1/2 kx squared, but our x is just the amplitude. So we'll plug in 1/2 times our spring constant, which was given, 400 newtons per meter, times the amplitude, which is 0.5 meters from the graph, and we square that, and get the initial energy is just 50 joules. So it's not moving when its position is the farthest away, so when it's at the amplitude for that given oscillation. So it's not moving when it's at time equals 0. It's also not moving here, or at any of the peaks and troughs. So this is time equals 0 seconds, time equals 2 seconds, 4 seconds, 6 seconds, and 8 seconds. Now for the times where it is at its equilibrium position, well, that's just when x equals 0. So x equals 0 will occur at 1, 3, 5, 7, and 9. So this is time equals 1 second, 3 seconds, 5 seconds, 7 seconds, and 9 seconds. Okay? And now finally, we want to find the energy lost during its first full oscillation. So its energy was initially given by the amplitude at time equals 0, but now after the first full oscillation, it only made it up this high, so at time equals 4 seconds. So what we can do is, to find the energy lost, we can take the energy at time equals 0 that it started with and subtract the total energy when it was at time equals 4 seconds after its first full oscillation. So this is just equal to E naught, the energy that we got at time equals 0 from before, minus the energy given at 4 seconds. So this is 1/2 k x squared, where x is the amplitude at 4 seconds. So this will be 50 joules minus 1/2 400 newtons per meter times our amplitude at that point, or 0.35 meters squared. So this will give us 50 minus 24.5, or the difference is 25.5 joules. The next problem, the period of oscillation of a block attached to a spring is 3 seconds. Determine the period if the mass is doubled, the mass is cut in half, and the amplitude is doubled, and the spring constant is doubled. So first off, we're given the period of oscillation, which is 2 pi times the square root of m over k. Okay, so this is going to be our base equation. And now we want to go through all of these scenarios. Okay, so what we want to do is we want to write an expression for the period as is, and then we want to write another expression for the period when it changes. So we're going to get a T1 and a T2, and then we can use proportional reasoning. So for the first scenario, our mass, so M2, what we change it to, is going to be twice the original mass. Okay, so if we double the mass, it's going to go to twice what it was before. Okay, so now I can write T1 over T2. Well, T1 is just going to be 2 pi times the square root of M1 over K, so we're not going to touch K. And now I can divide this by my expression for the period after I change the mass. So now I have M2 over K. So these are the exact same expressions, except I have a different period and a different mass. And now what you notice is 2 pi's will cancel. My square root of 1 over k and my square root of 1 over k will cancel. And this leaves me with the square root of m1 over the square root of m2, which is really just square root of m1 over m2. And now I can take this relationship that was given to me and I can plug it in. So if I do that, I get T1 over T2 is equal to the square root of M1, and then for M2 I'm going to put 2 times M1. So that means M1 and M1 are going to cancel. This gives me square root of 1 over 2, or 1 over square root of 2. Okay, since square root of 1 is just 1. And now I can solve this. So I will get T1 is equal to T2 divided by square root of 2. But I want to see how the period changed, so I'm going to write this as T2 is equal to the square root of 2 times T1. Okay, so now my period after doubling the mass, which is T2, is equal to square root of 2 times what it was before. Okay, so it changed by a factor of square root of 2. Okay, so I'm going to write that one here. And now we can go back and do the other cases. So if I just erase my work, this is going to change. Okay, so now my mass for part B, my mass is going to be cut in half. So now M2 is going to be half of M1. So I can do the same thing, 2 pi times square root of M1 over K divided by 2 pi square root of M2 over K. Okay, so again, these are going to cancel, square root of K's are going to cancel, and I get square root of M1 over M2. And then if I plug in, I get square root of M1 divided by M1 over 2. And so my M1s again are going to cancel, but now this 2 is going to come up in the numerator. So this is just going to be square root of 2. Okay, so now if I solve, I will get T1 equals the square root of 2 times T2, so it's backwards now. But again, I want to see how the period changed, so I'm going to write it as T2 is equal to 1 over the square root of 2 times T1. Okay, so this tells us the factor by which our period changed. So T2 is 1 over square root of 2 times the value it was initially. Okay, and so now let's go back and do part C. So now we want to double our amplitude. So A2 is going to be twice what it was before, A1. But if you write your expressions for the period, what you see is there's no dependence on amplitude. So if we leave the mass the same and we leave the spring constant the same, then this is just going to equal 1, and T1 will equal T2. Okay, so the amplitude will not affect the period. So T2 is equal to T1, and this is because there is no dependence on the amplitude. Okay, so let's go back and do the last one. Maybe I can leave that actually. So now we want to take our spring constant, K2, or K1, and double it. So K2 is going to be twice K1. And so if we plug that in, this is going to be K1 and K2. So our 2 pi's will cancel. Now our square root of M will cancel. And we're left with square root of 1 over K1 over square root of 1 over K2. So I'm going to take square root of 1 over K1 times the square root of K2 over 1. This gives me square root of K2 over K1. Okay, and now if I do my substitution, just rewrite this, T1 over T2 is square root of, for K2, I'm going to plug in 2K1. So 2 times K1 over K1, so my K1s will cancel, and I get square root of 2. So T1 is square root of 2 times T2, or T2 is 1 over square root of 2 times T1. So now if we write that, we get T2 is 1 over the square root of 2 times T1. And so doubling the spring constant, what we got for part D, is the same thing as cutting the mass in half. So these are the same, and that's reflected in the fact that mass is in the numerator and the spring constant is in the denominator. Changing one will have the inverse effect of changing the other. In the next problem, we have an oscillating mass of 45 grams that has a position given by the function x of t is equal to 0.05 meters times cosine of 12t minus pi over 2, where t is the time in seconds. Determine the amplitude, period, spring constant, phase constant, maximum speed, and total energy. Okay, so first, let's write our generic equation. We have x of t is equal to a cosine of omega t plus some phase, some offset. Okay, so I'll write this as phi naught. Now, all we need to do is to compare this formula with our formula for the position of an oscillating mass. So 0.05 meters times cosine of 12t minus pi over 2. So just by direct comparison, our number in front of the cosine is our amplitude. So A is equal to 0.05 meters. The period, well, we don't have the period here, but we have omega, and that can get us the period. So omega is going to be equal to 12, so it's in front of t, and omega is measured in radians per second. Okay, our formula for omega in terms of the period is 2 pi divided by t, and so if we want to solve for t, we just take 2 pi divided by omega, or the period is 2 pi divided by 12 radians per second. And that gives us pi over 6 seconds, or 0.52 seconds. So I'll write that over here. Pi over 6 seconds, or 0.52 seconds. Now we want our spring constant. So since we found omega, we can also use our expression for omega, which is equal to square root of k over m. So that means omega squared is k over m. So k, just multiplied by m, will be m omega squared, or 0.045 kilograms times 12 radians per second squared, or 6.48 newtons per meter. So K, 6.48 newtons per meter. Then we want to find our phase constant. Well, our phase constant is just phi naught. So here, if we just compare, it is minus pi over 2 radians. And then our maximum speed, just give myself some room, our Vmax is the amplitude times the square root of k over m, or this is just a times omega, and this is 0.05 meters times 12 radians per second, and that gives me 0.6 meters per second for Vmax. And then for the energy, well, the total energy when it's at the amplitude is just 1/2 Ka squared, since there's no kinetic energy. So this is 1/2 6.48 newtons per meter. We found K before. The amplitude is just 0.05 meters squared, or when we square that, and then we plug this in, we get 0.0081 joules, or 8.1 times 10 to the minus third joules. In the last problem, we have a simple pendulum that is 0.3 meters long with a 0.75 kilogram mass at its end, and it is released at the same time that a rock is dropped from atop a 55-meter tall building. Determine the number of full oscillations the pendulum will make by the time the rock hits the ground. Okay, so this pendulum is 0.3 meters long, and the mass of the pendulum is 0.75 kilograms. So it gave us the mass of the pendulum, but it turns out the period of a simple pendulum only depends on the length. So it's 2 pi times L over G. So if we plug in, we get 2 pi times the square root of 0.3 meters over 9.8 meters per second squared. And that gives us a period of 1.1 seconds. Okay, so every 1.1 seconds, the pendulum will oscillate, and we need to figure out how many seconds we have until the rock hits the ground, and then we can figure out how many times this happens. So if we use kinematics, the height of the building, delta y, we know that. We know it's going to start from rest, and then we're looking for how long it's going to take. So we can use this expression. We need one with time in it. Okay, and v naught y is just going to be 0. So we can solve for t pretty easily. This is just going to be 2 times delta y divided by g, or minus 2. And then we take a square root. So square root of minus 2, Our delta y is going to be minus 55 meters because we're moving down. Okay, so it's negative and divided by 9.8 meters per second squared. This gives us a time of 3.35 seconds. And then we can just see how many periods are in this amount of time. So we do time divided by the period, or 3.35 seconds divided by 1.1 second. And that's going to give us 3 full revolutions. Okay, so the pendulum has time to oscillate 3 full times before the rock hits the ground. So I hope these problems in periodic motion and simple harmonic motion were helpful, and I'll see you in the next video.